Okay, let's move to the second example, and it's a very famous one. It's known as the Monty Hall problem, which comes from the show Let's Make a Deal. Many of you probably don't know it, but it was an old show, and in that show there was a contestant, a person that was close to winning a big prize, and that contestant was presented with 3 doors, and behind one door there was like a big prize, like a car or like a cruise ship vacation, something valuable, and behind the 2 other doors there's a goat. So what needs to happen is that the contestant needs to make an initial selection. And then Monty Hall, the game show host, opens a different door that reveals a goat. So that leaves 2 doors still closed, one of which hides the car. So Monty Hall then asks the contestant whether they want to switch from their original choice to the other closed door, or whether they want to stay. And many people now think that the probability of the car being behind either of the 2 remaining closed doors is 50-50. But that can be shown but that is wrong, and that can be shown using Bayes' theorem. Okay, so in order to illustrate that, let's just assume that the contestant chooses door 1 and Monty reveals a goat behind door 3. Okay, so we have like 3 doors. Door 1, door 2, and door 3. Okay, so the candidate chooses 1. So this is the selection. So this is what the candidate chooses. Then, if the big prize, the car, were behind door 1, Monty could either open door 2 or door 3 to reveal a goat. So let's say the goat is revealed behind door 2. So that means that the big prize is now either behind door 1, which the candidate chose, or it could be behind door 3. So the Monty Hall, the game show host, is now asking the contestant, do you want to switch? And again, most people would think, there's no point in switching, it's a 50-50 chance. But that's wrong. Switching would have now a higher probability of winning than staying. There's no guarantee that you win, but let's say if you were able to play that game 100 times, then switching would statistically make you 66 times win, and it is the better choice. Before we go into the statistical notation, I want to give you first the intuition behind that, and I want to do that in Excel. So in Excel we can actually simulate the game, and what I want to do is I'll play the game, let's say 1,000 times, and in the first column for each game I have a column prize in door. Okay, so the big prize could be either in door 1, door 2, or 2, 3. So I simulate that by telling Excel, select a random number between. The command is rand between, so 1 and 3, 1, 3. Okay, so in the first game there is a 3. But now we play that 1,000 times. So I copy this down 1,000 times. Okay. And you see, so sometimes it's 2, 2, 2, 3, 2, 1. So it's really random. And in Excel, whenever I click on something, like I do here 1, it recalculates always everything. So don't get confused by those numbers changing all the time. So now let's assume candidate chooses door 1. So candidate choice. And it's always 1. So the way you can think about it now is like this. You know there is a 1/3 probability that the car is behind door 1, door 2, or door 3. Well, if the candidate always sticks with their choice of 1, well, then the choice of winning is 1/3, right? So what happens to the other 2/3? Well, that means that if you don't switch, you lose 2/3 of the time. But in reverse logic, it would also say that if you had switched every time, you will win 2/3 of the time. Okay, let's just illustrate that. So the candidate wins, let's just call that wins. And again, don't get confused that whenever you click here somewhere, the numbers change. But the candidate wins whenever, if the price in the door equals to the 1. Then give it a 1 and the 1 signals that's a win. Otherwise it is 0, which means a loss. Okay, so in the first one we lost, and then here in the fourth game, 1, 2, 3, 4, we would have a win. And let's do that just for all. So those are the wins. And we can see what are the losses. So a loss occurs whenever, if under the win, if that is equal to a 0, to a 1, then, well, whenever the candidate, actually let's say it this way, whenever the candidate doesn't win, so whenever that is, it doesn't really matter how we do. So let's say if this is 0, so that means the candidate did not win, so it is a 1, because then the candidate loses, otherwise it is a 0. So now we see whenever the candidate doesn't have a win, it means the candidate accumulates a loss. So, and whenever, so here for example now, the candidate wins and it's not a loss. Okay, so now let's sum up the wins. Sum of wins, sum of losses. Okay, and again, don't get confused that things always change. So the sum of wins is simply the sum of all the wins. So that means there are 356 wins. What about the losses? So now we sum up the losses. Okay, so it's, and you see whenever you click on something, it changes. It's always roughly, you lose, you win 1/3 of the times and you lose 2/3 of the time. And again, this implies that if you had changed every time, instead of sticking, instead of losing 641 times, in this case you would have won 2/3 of the times. Okay, so that's the idea behind, but now let's derive it using Bayes' theorem. Okay, the question is, what's the probability that the car is behind door 1 given that Monty opened door 2? And we need to compare that to the scenario that the car is behind door 3 given that Monty opened door 2. So in this case, we can already start and we can acknowledge that, okay, the car could be with a probability of 1/3 behind door 1 or with a probability of 1/3 behind door 3. So that is pretty straightforward. Okay, so, but what's the probability that when the car is really behind door 1, then what's the probability that Monty opens door 2? Well, that means because the car is not in door 2 or door 3, could reveal a goat in either one because both door 2 and door 3 have a goat. So that is 1/2. But here, let's assume the car is actually behind door 3 and the candidate chose door 1. That means Monty Hall cannot open door 1 because that's the one that the candidate chose. And it cannot open door 3 because that would reveal the big prize. So Monty needs to open door 2. So that probability is 1. Okay, so now we need to think a little bit, what's the probability that the door 2 will be opened? Okay, and this we need to know. Okay, we can do maybe a little table here. So we know that the big prize, let's make here a table. So the big prize, okay, so big prize, let's say the car, could be behind door 1 with probability, let's say car, okay, car, let's write it car in door. So or big prize, prize in door 1. Prize in door. So the prize could be either in 1, 2, or 3. Okay, so what's the probability for each? So the probability is for each 1/3, 1/3, 1/3. Could be in either one. Okay. So now what's the probability that, Monty opens door 2? Door 2, well, that depends on given where the car is, right? So a car could be in 1, 2, or 3, or the big prize. So that depends on the car. So, okay, so if the car were in door 1, then Monty could open either door 2 or door 3, so can flip a coin. So then the probability of opening door 2, if the car is in 1, that would be 1/2. Well, what if the car were in door 2. So then remember that Monty, the candidate, has chosen door 1. Well, if the car were in door 2, Monty couldn't open it, so it would have to choose door 3. So the probability now that if the car is in door 2 and the candidate has chosen door 1 is 0. And what's the probability that if the car is in door 3, then Monty would have to open door 2 with probability 1, because the candidate chose 1, door 1, Monty cannot open that one. And in door 3, that would be the car, that he cannot reveal that one either. So there's a 1% probability that the game show host will open door 2. Okay, so now we have to sum up all those probabilities, so which is the probability of each door times the probability of door given that the car is behind that door. So that's 1/3 times 1/2, so that's 1/6. 1/3 times 0, that's 0, and 1/3 times 1, that's 1/3. Okay, so this is 1/6 plus 2/6. So the probability is 1/6 plus 2/6, which is 3/6. So this is always 1/2. So this is the a priori probability if knowing under the scenario that the candidate chose door 1. So we know that there's always a probability that Monty opens door 2 with a probability of 1/2. And that is what we just derived here. So what we did is the sum of, oh, let's write it down more. So the probability Monty door 2, what we just did is the sum of the probability that it's behind door I times the probability, actually I don't have to do that, times the probability of door 2 given that the car is behind door I. So what's the probability of I, that it's behind each door, times the probability that Monty opens the second door given that the car is behind that door. Okay, so this is always 1/2. And so now we can do the math. So here 1/3 times 1/2 over 1/2, well, that cancels out. We are left with 1/3. Here we have 1/3 over 1/2, so half over 1/3 is 2/3. So if we divide them in 1/3 divided by a half is 2/3. So that's what we get here. And this is the formal proof applying Bayes' theory, but I think the intuition is also pretty clear, like when you just simulate it in Excel, it also should be clear. Okay, so let's just stop here, and then in the next one we discuss another application in the field of decision analysis. But let's just stop here.